In this video, I'm going to look at the problem I've shown on the screen here, which is a polyprotic acid that we're going to be looking as we titrate it with a strong base. I'm specifically going to be looking at a bunch of different cases that come up. So we'll be covering the 0 milliliters added case, so what do you do when you first start the titration? We'll be covering a couple where we're in buffering regions. We'll be covering at what we do at the equivalence point. The only one I won't be doing in the video is this one right here, the 20.1. I've got a separate video with that one, but the rest of them we'll do here. So let's start with the 0 milliliter added case. So the idea behind this reaction is, first we want to think about what equilibriums matter for this whole problem. Now, rather than writing out the whole thing for orthophthalic acid, I'm just going to write H2A. So in general, we have two equilibriums that matter for our reaction. We have H2A plus water is an equilibrium with HA minus plus H3O plus. That has a Ka with it. Ka1, which I looked up, and it is 1.12 times 10 to the negative 3. Then it can dissociate a second time. You have HA minus plus water is an equilibrium with A2 minus plus H3O plus, which is a Ka2 of 3.91 times 10 to the negative 6th. And technically you have a third equilibrium that matters as well, which is water. Remember, you still have a Kw, H0 plus and OH minus are connected to each other. Both of these Kas are large enough here that this is going to end up being the main source of your hydronium ions, so you don't have to worry about how much neutral water is contributing in this case. So that is something you might have to think about in other types of equilibrium situations, but we're not doing it within these titration problems here. So the way we do a lot of these problems is we try to find places where we can ignore certain parts of the equilibrium and say, okay, this part just doesn't matter, it's not going to form. And those approximations make these problems much more reasonable to solve. So our first case we're going to look at is 0 milliliters added. So in this case, you start with all H2A. And the idea, if you look at the Ka, is H2A is going to convert to HA minus, but not a whole lot of it. So if you're not making very much HA minus, and you were to plug it into Ka2, very little HA minus would make an extremely small amount of A2 minus. It's going to make a small enough amount that we're going to make the assumption that it's not going to make enough to contribute towards changing any of our values, and we're just going to worry about the top equilibrium. This is reasonable as long as K1 and K2, usually if they're like different by a factor of 1,000 or so, you're fine. Even when you're in the hundreds, they are sometimes, but like as you get closer and closer, that becomes less true. And you can always check by plugging numbers in to see would it change things if I change this concentration, how much A2 minus would you actually make? Is that enough to remove enough HA minus to change anything? But for this one, we're going to assume only the top equation matters because we're predominantly H2A. We're only going to convert it to HA minus. So that means we only have one Ka statement to work with, which is Ka equals HA minus times H3O plus divided by H2A. Now here, I'm going to make two additional approximations, which are both fairly reasonable in this case. The first approximation is I'm going to assume that every H3O plus that I'm making in this reaction is going to come from this top reaction, which means each H3O plus will also make an HA minus. If I'm not worried about the H3O plus from Kw or from Ka2, then the amount of H3O plus I'm making all comes from the dissociation of H2A. HA minus and H3O plus should be equal. This would not be true if Ka2 was a significant contributor or if Kw was a significant contributor. So that's the approximation I'm making, that only Ka1 matters in this case. In that case, I can simplify this by saying that it is H3O plus squared. Then in the denominator, the other thing I'm going to say is that when we form HA minus, not very much is going to form compared to H2A. For this reason, I'm going to say we're not going to lose very many H2A molecules compared to what we have at the start. And therefore, the concentration is going to stay constant. So I'm going to say this is still 0.200 molar. Note that if you make enough HA minus, where that would change by more than a factor of, let's say, 5 to 10%, I'm okay with 10% for our exams, 5% depending on which class you're in. Once it starts making enough, then that stops being true. So you can always check by seeing how much H3O plus did I make? Okay, how much HA minus must I have had? Is that enough if I subtracted that from my concentration of H2A that it would change it in terms of how much I care about how much error I have? So that's something you should always check with these problems because sometimes that won't be true. So we plug in our Ka1, 1.12 times 10 to the negative 3. From there, I'm going to multiply both sides by 0.2, take the square root of both sides. That will give me a value of H3O plus equal to 0.0150 mole. Wait, did Let me make sure. I'm going to check on my own calculator. I did this like a couple days ago. I just want to make sure. second square. Oh, yeah, that is right. It just came out so nice and neat. I didn't believe it could be possible, but it was. See, I know, because it's like 0.014966. So, yeah, rounds up to 0.0150. And then we find the pH of that, and it's 1.82. So that is our pH when we're working with something that's just 0 milliliters. We just treated it like a monoprotic acid, with the Ka1 being the one that mattered. We solved it the exact same way. So let's now go to the 10 milliliter case. So I'm going to keep using both these equations. I'm going to go to the next slide, but we're going to keep using them throughout. I'm going to keep referring back to them. I may go back to this slide occasionally and do that, but I need some more space. So at 10 milliliters added, the first thing to note is there are two ways to solve this. So I'm going to point out a fast way, then I'm going to do it a slower way just in case you didn't notice this, because it's never wrong to do it the slower way. But if you go back to the problem, you'll notice that if you calculate the equivalence point is at 20 milliliters. That means 10 milliliters and you can do that by checking the number of moles of acid compared to moles of base. You can figure that out on your own. What that means is if you're at the half equivalence point, you can just say pH equals pKa. 1, look up pKa1. It's take the negative log of 1.12, you're done. So, for example, on my assessment, that's fine. Just make sure you're actually at the half equivalence point, because if you're not at the half equivalence point, you just removed a lot of work, and I can't give you partial credit for things for that. I'll give you a few points to give the idea, like as long as it's reasonable what you were. But doing that means you're not showing work, so make sure you're right about that statement. But if you are, it's perfectly fine. You don't have to show anything else. But let's say you didn't notice that. How would I solve this problem if I didn't notice that quick shortcut of, hey, I'm halfway to the equivalence point, pH equals pK? Well, first we're going to do a calculation that I'm going to use a bunch this whole problem, the rest of the problem. I need to know how many moles of H2A I started with. So we had 10 milliliters. And it was 0.2 molar. And so that gives us that we have 0.002000 moles of H2A at the start. So I'm going to keep using this number for the rest of the problems rather than recalculating over and over again. So now I want to know how many moles of H2A I have left and how many moles of HA minus I have formed. The reason I know these are the two I'm interested in is I have not yet reached the first equivalence point. This means before you reach the first equivalence, every time I add a sodium hydroxide, that OH minus on sodium hydroxide is going to grab a proton off of H2A. And it's going to grab the most acidic proton and pull it off, and then it's going to keep doing that to H2A over and over again. This is because the Kas are sufficiently separated that first proton is way more acidic than the second one. So I expect that sodium hydroxide is going to constantly be grabbing one proton rather than pulling a second one off and forming A2 minus. And even in the event where it might have done that, it would probably reform HA minus relatively quickly because of the different acidity levels of those protons, and I'm saying that based on the pKa values. If those pKa's were really close together, that statement would no longer be true, and it wouldn't make a clean titration anymore. So if you were working with a molecule that had two pKa's that were like, let's say, negative first and negative second powers, they were relatively close, you don't get a nice neat titration like that, and then the titration problem becomes more complicated. But we're doing something where they're at least, this one they're 3 orders of magnitude apart, we're definitely fine to say that. So I want to know how many moles I have left. So moles of H2A remaining. Well, we know what we started with. We started with 0.002000 moles, and then every molecule of sodium hydroxide removes one of these. So I'm going to subtract the number of moles of sodium hydroxide since it's a 1-to-1 reaction. We've added 10 liters, and it is 0.1 molar. And so when you do that, I'm going to get I've used up exactly half. So 0.00100 moles of HA minus remain, or H2A remain. I'm going to make that actually look like H2A. So that's how many moles of H2A we have left. At the same time, we can also use this to calculate the moles of HA minus formed. The idea behind this is that every molecule of sodium hydroxide we add turned one of the H2As into an HA minus. So for every H2A you lose, you form an HA minus. So that would be 0.10, that's a decimal, not a negative, 0.100 liters times 0.100 moles per liter, representing how much sodium hydroxide I added, and all that sodium hydroxide turned H2A into HA minus. So that's 0.001000 moles of HA minus. Now, since these are both in the same solution, I can simply leave this in moles and put it into Henderson-Hasselbalch. Remember, this works because since they're in the same container, they would have the same volumes. When you divide them by each other, base over acid, they would cancel out. That's why you're able to do this. So when I write out Henderson-Hasselbalch, I get pH equals the negative log of pKa. Sorry about that. 1.12 times 10 to the negative 3. Plus the log of the base over the acid, And so base in this case is HA minus 0.001000 divided by H2A, 0.001000. And so you get the log of 1. Log of 1 is 0. That's why you can say pH equals pKa. So you get a pH of 2.95. And that's your answer for our 10 milliliter case. So we're done there. Let's move on now, and let's look at the 20 milliliter case. So at the 20 milliliter case, I'll just erase this slide. I don't need this one anymore. Erase all ink. So for the 20 milliliter case, that's at the first equivalence point. Importantly, unlike the monoprotic acids, the polyprotic acids will have different circumstances. So in the case of the first equivalence point, that means you've turned all of your H2A molecules into HA minus because you've added exactly enough to remove one proton from all of them. So you have 0.002000 moles of HA minus. And before we start worrying about equilibrium, none of the other two species, the H2A or the A2 minus. Sorry about that. I'll pause the recording next time that happens. I at least muted myself. Okay. What's important here is HA minus occurs in two different equilibriums. It occurs in the Ka1 and the Ka2. What that means is it's got two possible species it could turn into when it's in high concentration. HA minus could lose a proton and form A2 minus. HA minus could gain a proton and form H2A. In those cases, we have an equation we could work on that we talked about in class related to dealing with, what is it? It's pH of something like NaHA, right? So if you had a sodium salt of an acid, in this case HA minus, that could turn into two things. It's amphoteric, so it could form H2A or A2 minus. Then we have an equation to solve for H3O plus. Your textbook in Scoog goes through a proof of why this works, and it only works because there's no H2A and no A2 minus initially. If you had some of those initially, it would affect this calculation. You couldn't make this approximation. You need to refer to my video that I've recorded on how to deal with close to equivalence point, but not at equivalence point problems. But for this easier one, we can literally just say H3O plus equals the square root of Ka2 times the concentration of our acid. No, it doesn't matter that it's sodium specifically. It could be, you could have been using potassium hydroxide. You get the same answer. That doesn't matter. It's just the idea that you wouldn't have it floating around by itself. It's a negative charge, there's positives around, so they'd be associated with each other. You could also use this equation if you used a sodium salt that had this compound. You use something like some of the sodium phosphate buffers, right? H3PO4, you could start removing protons, put sodium on it. You can use this equation for that too. So, plus Kw divided by 1 plus the concentration again, divided by Ka1. Note that there is a simplified version in your Scoog text that talks about when sometimes you can just take the square root of Ka2 times Ka1. That requires a couple of that requires that your top value, the concentration times Ka2, be such that it is much bigger than Kw, and the concentration of the acid or HA divided by Ka1 can't be very large. Or, right, because you end up, the problem is if the 1 matters a lot, that changes it too. So it's easier just to use this equation, I find. The additional approximation, I don't find that helpful. Although you can use it if you understand when and how. So, with that, I just have to plug a bunch of numbers in. So these are nice in that sense. Of the 20 milliliter case, you're at an equivalence point, you just plug numbers in. So Ka2 is 3.9. Is that right? Yes. 3.91 times 10 to the negative 6th. You multiply this times the concentration, which I forgot to I found in my notes, but not right here. The concentration is we have 0.002000 moles, because we calculated that in the last part. That's of HA minus now. But our volume's different. We've added 20 milliliters, so we've got 30 milliliters, or 0.03000 liters. So that takes us to 0.0667 molar. So this will be 0.0667 plus, since we're going to assume we're at 20 degrees, 1.0 times 10 to the negative 14th. I ended my square root bar early. There we go. Divided by 1 plus the concentration again, 0.0667, divided by 1.12 times 10 to the negative 3. As a reminder, the general case is here. K1 is the version where whatever HA stands for, HA minus, is becoming H2A. So it's when it's gaining a proton. And Ka2 is when whatever you're representing with this HA minus is losing another proton. So in the case of a triprotic acid, it might be Ka2 and Ka3 of a triprotic acid become Ka1 and Ka2 here. So this is about that term HA, what it represents, whether it's the gaining a proton or losing a proton equation. So you plug all that stuff in, you get the H3O plus is... I thought I was all better. Guess not. The 6.56 times 10 to the negative fifth molar. You take the negative log of that, you get pH equals 4.18. So the nice thing is, doing equivalence point calculations with polyprotic acids is pretty easy too. It's honestly easier than when you do the monoprotic, because it's just put a bunch of stuff in an equation, you can go. Your textbook goes through the particulars of why you can do this, which are perfectly fine for you to go through, but if you can't repeat that exact derivation, we'll be all right. Now, we have two other problems to solve that are somewhat short. Let's look at those now. Erase all ink. So I want to look at 32 milliliters added. So now we are past the first equivalence point, but not to the second one. Since first equivalence was at 20, second was at 40. Also, we're not at a half equivalence point, so I can't just do a quick, at 30 milliliters, pH equals pK2. Can't do that. I also know that when I get my answer, I should have more base than acid because I'm past the half equivalence point. I've added enough base that I should have more base molecules than acid molecules. So there should be more A2 minus and less H2A, or less HA minus. There's basically no H2A. I shouldn't use the word basically because basicness of solutions, that's fun. So the way to think of this problem is your first 20 milliliters was dedicated to, not dedicated, but what was happening was H2A was becoming HA minus. So the first 20 milliliters of sodium hydroxide don't affect the concentration of A2 minus at all. So 20 milliliters converted all the H2A molecules into HA minus. You now have, at 20 milliliters, you've got 0.002000 moles of HA minus. Now the next 12 milliliters start converting that A minus into HA minus into A2 minus. So these 12 milliliters are now going to start taking some of the HA minus and converting it into A2 minus, but not all of it, because you'd have to add another 20 to get to all of it. Now, let's go with that now. So what does that mean? That means my moles of HA minus, we know at 20 milliliters we had 0.002000 moles, but then we lost some over the next 12 milliliters, and so those 12 milliliters of 0.1 molar sodium hydroxide are going to have gotten rid of some of this, and so that's going to give us 0.000800 moles of HA minus. And then how many moles of A2 minus did we form? Well, that comes from the 12 milliliters of sodium hydroxide. So you notice with these problems, a lot of it's about being able to identify what it is you need to be able to, like what's happening at different steps to figure out what calculations to do. So to be able to figure out, I just need to multiply this by the 12 milliliters, not the full 32. So being able to figure out how to stepwise break down your problem. And that gave us 0.001200 moles of A2 minus. We have more base than acid. That's good, what we would expect. Again, we can use Henderson-Hasselbalch. We're in a buffering region. And because we're using Henderson-Hasselbalch, we don't have to calculate the concentrations. We can leave it in moles, and we'll be fine because they're in the same container. So we've got the negative log of Ka2 plus the log of 0.001200 over 0.000800. That gives us a pH of 5.79. There we go. 32 milliliters added. Got two more cases. I think I said two last time. There's actually still two because I've got to do both second equivalence point and past equivalence. So let's look at 40 next. And hopefully I don't cough too much before we get done. Sorry for the quick breaks. I'm at least learning to press the mute button on my mic because I know you don't need me to cough into this. And I don't have the energy to edit this video out. So we'll just have short breaks where I cough. So 40 milliliters added. Stay on task. This is already long enough to record. So at 40 milliliters, you've reached exactly two equivalence points. 20 milliliters brought H2A to HA minus. 20 more brought it from HA minus to A2 minus. So here we have 0.002000 moles of A2 minus. Now, unlike HA minus is amphoteric. It could form H2A or A2 minus. A2 minus doesn't have like some negative HA3 minus. It can't lose another proton, so it can only form HA minus. That means we can't use that equation for a shortcut. This is instead a weak base problem. The A2 minus is a conjugate base. It can't act as an acid, so we're only going to have to look at the conjugate base form. Since I only got one of them to start, I do need to find its concentration. I then need to find Kb and solve with that. So the concentration is 0.002000 moles. I write that number a lot. This problem divided by the volume, which is now 50 milliliters. And that'll give us 0.0400 molar. And then if we write our new equation, we now have A2 minus plus H2O is in equilibrium with HA minus plus OH minus. And if you solve for Kb of this, Kb2, you will get, try to read my own writing, 2.56 times 10 to the negative ninth. Remember, that's just Kw divided by Ka2. So that's my Kb2. And so if I rearrange that equation, or just set up that equation, Kb2 is equal to HA minus times OH minus divided by A2 minus. We're going to make some approximations similar to the 0 milliliter case with the acid version. So I'm going to assume, and that's fairly reasonable even with this Kb, that all of the OH minus I'm going to see is going to come from the dissociation of A2 minus taking a proton from water and forming it, and forming HA. That means the number of HA minus molecules will equal the number of OH minus molecules here. I'm also going to assume this won't happen a whole lot, so that the A2 minus isn't going to decrease a whole lot in concentration, so I'm going to treat it as just 0.0400 molar. When you get your OH minus, make sure to go back and check. That's definitely true in this case. Kb is so small, there's not going to be a lot of this. We'll definitely be fine. Like, this is what I'm very confident of, like, I wouldn't have to check it, but it's a good idea if you're not used to looking at the Kb's and being really sure, especially depending on what your concentration is, what's reasonable for that. So to make those approximations, I get OH minus squared divided by 0.0400 equals 2.56 times 10 to the negative ninth. I multiply by 0.04, take the square root. I get that OH minus is equal to 1.01 times 10 to the negative fifth. So if I took 0.0400 and subtracted 1.01 times 10 to the negative fifth, the number basically doesn't change. My calculator rounding, I'm going to end up rounding that away and not even noticing. So yeah, it does not change it enough that I'm worried about it. I can take the negative log of this, get the POH, do 14 minus that. When I do that, I will get that the pH equals 9.01. So that's the 40 milliliter case. We're almost done. And I'm ready to be done too. So let's go to the 45 milliliter case. The excess base case. So 45 milliliters added. Here, we don't have to worry about all of it, right? The first 40 milliliters turned H2A into HA minus into A2 minus. So those 40 milliliters of sodium hydroxide got used up. All that OH minus is gone. But we added 5 more milliliters, and so that's the part I'm worried about. There's extra OH minus, and it doesn't have anything to steal a proton from anymore, so, to react with, to like pull it off one of those acids. So I want to know how much OH minus is still floating around here. So we have 0.005 for the mill. Yes, I can do 5 divided by 1,000. Had to make sure. So that's how much we have of excess times the 0.100 moles per liter. But I need a concentration here, so I divide it by the volume, and we've got 55 milliliters, 45 plus 10. So to do that, I get 0.00909 molar. Take the negative log of that, do 14 minus that, you'll get a pH equal to 11.96. Makes sense. We're in the excess base region, we should get pretty basic pretty quickly. Based on the concentration of our base we're added, we'll determine what we're rising up to. So hopefully all those examples help out some. That goes through all the possible cases in the polyprotic acid outside of that one that I did another video on. But between the two videos, I've looked at all those cases. You'll notice in a lot of ways, it's very much like problems that are monoprotic. It's just you have to put a little more thought into it sometimes of which equations are relevant to think through what approximations I can make. Most of the times when this gets hard is when one of those approximations gets weakened in some way when we can't make it and we have to do more calculations. But outside of that, these problems are fairly straightforward. Also, I'll note that this is easier than it might be otherwise. I've ignored activities in all cases. We haven't looked at how would that have changed things. How do we have to think about that? We haven't looked at that in any of these cases. So for all of this, in case you're watching this at some other date or someone else that you're not in my class right now, you might go, hey, wait, if you thought about activities, some of these parts could be more complicated, but we're not worried about that right now. So hopefully it helps out, and I hope you do well on your exam whenever you